So in this video, I'm going to talk about the imaging condition. So what is the imaging condition? Where does it come from? And how do we figure out when it is satisfied? Well, the imaging condition just says, let's say that I've got some object, which we usually draw as an arrow, and I've got some lens, or in general, any optical system, and let's say this is the optical axis. Then we know in general, there's going to be some image. There's going to be some image somewhere on the right-hand side. And what do we mean when we say there's going to be an image? Well, we say that these point sources, so let's take the point source at the bottom of this, this arrow. This arrow is just made up of a bunch of different point sources. It's going to radiate out spherical waves, and those waves are going to map to spherical waves on the other side, which instead of diverging are going to be converging, and they're going to converge to a single point. And so we've now mapped a point to a point, and this happens for all points on this object to all points on this image. And so we want to figure out, okay, well, if I have an object, then there is going to be some point at which these spherical waves all converge to form a perfect image. So if I weren't at this particular point, I might see a blob or a blur. I wouldn't see what I initially, my object. And so we want to figure out, well, what is this distance, SI, let's call it. So the distance, or sorry, SO, the distance to the object. And this distance, SI, such that we have a point source that maps to a point source, or we have a perfect image being formed. So how do we do this? Well, the easiest way is probably to use a ray transfer matrix. So we see that, well, we're going to be propagating a distance SO. So that's the first thing that happens in our system. We propagate a distance SO, and then we go through a lens. So this L is a lens matrix. And then we propagate another distance SI. And so this is our overall ray transfer matrix. I'm going to call this T. And so we want to know what restrictions are placed on T such that I have a single point source mapping to a single point source. And if it's an on-axis point source, then it's going to map to an on-axis point source. Well, we can express that using math. We can say that, well, my transfer matrix, if it acts on an on-axis point source, which just is, its x-coordinate is 0, and it has some range of theta, so it's got some arbitrary theta in, and this theta in can be anything, right? It can be here, it could be here, it could be here. It's anything in this point source's emission field, I guess you could call it. So, but the x-coordinate is 0, and we know that this has to map to, we said this point right here, wow, that's a lot of arrows, this x out is also going to be 0. So because if we trace out the ray, we know that it just goes straight through the system. It shouldn't deviate from the object to the image if we're just going straight along an axially symmetric imaging system. And we don't know what the theta out is going to be, so let's just write it as theta out. Okay, now if we write the full equations for this, so this is x out, we know that 0 is in general going to be equal to, if we just write out the matrix equations, t11 times x in, which is 0, plus t12 times theta in. Well, clearly this term is 0, so we just have t12 times theta in is equal to 0. And is this true? Well, I mean, theta in can be anything, right? It can be, it could be this middle ray, it could be some ray up here. Theta in can take any arbitrary value. And so this isn't going to be true in general unless t12 is equal to 0. And so this is actually the most general form of the imaging condition. Because if we've got some ray transfer matrix, it can be anything. We can propagate some distance, we can go through a lens, we can go through another lens, we can go through some weird optical system, and then we can get to our image. as long as the transfer matrix representing that system, as long as its 1, 2 component is 0, that's where we form an image. But this is a little unsatisfying because, okay, well, what about for this simple lens system? Ideally, we'd like an equation, a simpler equation that describes what goes on here. And so we just need to find that expression. We just need to solve for this transfer matrix. And so let's actually do that. Well, we know the propagation matrix. So our object propagation matrix goes on the very right-hand side, 0, 1. We know the matrix for the transfer matrix for a lens. It's just 1, 0 minus 1 over f, 1, where f is that lens's focal length. And then we've got our image propagation, or our image distance propagation. So this is our transfer matrix. So let's just solve for it. This isn't too bad. We can do this by hand. So let's combine these matrices first. So what do we get? 1 up here, and then 1 times s0 plus 0 times 1 is just s0, and then minus 1 over f. Let's see, minus 1 over plus 0, and then minus s0 over f plus 1. So that's those two matrices, and then our matrix on the left-hand side. And this is one of the reasons I like ray transfer matrices. They're a bit challenging to work with, but they're incredibly powerful, and they're relatively easy to multiply out. So what's this matrix? 1 minus si over f is this upper left term, and then this upper right term will be, what is this? SO, which is 1 times SO plus or minus SI SO over F plus SI. And then the other two we could math out, and let's just do that just for completeness. Then we've got minus 1 over F, and then 0 times SO plus 1 times minus SO over F plus 1. Okay, so this is our overall transfer matrix. That wasn't too terrible. And we said that this term, T12, has to be equal to 0. So let's solve for it. So, well, we have SO minus SI SO over F plus SI is equal to 0. And this is great, but, you know, it's a little ugly. So if we assume that SI and SO aren't going to be equal to 0, which would make our optical system a little weird to say nothing of what that would do to the math. Let's just divide everything by SI-SO. If we do that, we'll get 1 over SI minus 1 over F plus 1 over SO is equal to 0. And if we move over the 1 over F, we have the final form of our imaging condition. And so this is in terms of the lens focal length, the distance to the object to the left, and the distance to the image, which is defined as being to the right. And so we call this the imaging condition. And usually we know F, or we want to design F, but if this equation is satisfied, we will have an image formed. So a point source will map to a point source, and an object will map to an image. But this isn't the most general form, because this is for a thin lens in air. So if we don't have a thin lens, or we're not in air, then we need to use the more general form of the imaging condition, which is that T12 is equal to 0. And this one will never lead you astray. So if you have the transfer matrix for a system, you can set T12 is equal to 0, and then you can solve that equation, and that will give you where your image is formed. So thanks for watching the video. If you have any questions or comments, please feel free to post them down below. If you liked the video, please give it a thumbs up and consider subscribing to my channel, and I'll see you next time.